Okay, in this short video, I'm going to try to explain how to interpret coefficients when part of the model has been logged or when we have logs on both sides of the equality sign in our regression model. So to begin, we'll start with a model that's familiar to us. Let's look at this particular model here. We have 1x and 1y in the model, so it's the easiest or simplest kind of model that we look at. And we're used to interpreting the alpha 1 in a model like this. And alpha 1 is simply the change in y on average when x goes up by a unit. Okay, so it's the change in y from a 1 unit change in x. If we have other variables in the model, it would be the change in y on average from a 1 unit change in that particular x, holding the other x's constant. But what about when we have natural logs in the model? For simplicity, I'm just going to suppress the error term, and we don't have to use the on average and expected value language then, and I think it'll make the conversation a little bit simpler and easier to follow. So let's suppose, first of all, that we have a log on the left-hand side of the model. So we want to know specifically, for example, what the meaning of that alpha is, how we should interpret it. Then we'll run through a double log model where we have logs on both sides, and we'll look at the other form of semi-log model where the log is on the right-hand side. Okay, so in order to make this argument, we're going to appeal to a mathematical concept called the total differential of a function. And the total differential is particularly simple in the bivariate case. That is the case where we have 1x and 1y. So it's so simple, in fact, or so basic, it's almost like, why should we bother with this? Well, it turns out that it's actually helpful in understanding the meaning of these coefficients with logs if we know how to think about this differential. We use the total differential as an aside more extensively in microeconomics or macroeconomics when we have functions of several variables. So we have y equals some function of x1, x2, x3, and so on. But here we really are only going to use the total differential when we have a function of a single variable. Okay? So the definition of a total differential is given by this expression right here. And I'm going to think about these dx's and these df's as small changes in x and f, for example. And I'm going to focus on f prime as the derivative of f with respect to x. So we're thinking about f prime as being the change in the value of the function when x goes up by an infinitesimal amount. Okay? We're thinking about dx as some small change in x, and df as some small change in f that results from some change in x. Okay? And this relationship here in the red box is called the total differential of f. So as a specific example, if we have f of x equal to the log of x, then from a previous conversation we know that the f prime in this case is just going to be 1 over x. So that's the derivative of this function log x with respect to x. It's really the function that describes the slope of the log at some given x value. Okay? To plug this into the total differential language, we follow this formula here. So we end up with df equals f prime, that's 1 over x, times dx. Okay? So we can think about 1 over x as the rate of change of f with respect to x, and when we multiply that times dx, okay, we get the total change in f that resulted from a change in x. That's one way to think about it. So let's go back to the problem at hand. We have a log on one side of the equation, okay, and we want to know what the interpretation of alpha 1 is in this context. Well, alpha 1 can be thought of as dy d log x. So it's as if we're thinking about log x as some variable z, and we're thinking about this as dz, but it's really just the log of x, so I'm leaving it in there as the log of x. Why am I doing that? Because this d log x can be thought of as the total differential of the log of x. D anything can be thought of as the total differential of that anything, okay? So d log x in this case is going to be what? It's going to be 1 over x times dx. 1 over x times dx, or in other words, just dx over x. So I can rewrite this alpha 1 expression as dy divided by dx over x. Well, dx over x is the change in x divided by some x. So if I take the change in x and I divide by some initial x, it's almost as if it's a, what? Percentage change, right? If I take the change in x and divide by x, it would be a percentage change if I had multiplied that by 100, okay? It's right now it's in fraction form. It's the change in x as a fraction of some initial x. So if I take the change in x and divide it by x, and then I multiply it by 100, I end up with the percent change in x once it's multiplied by 100. But if I multiply the denominator of this expression by 100 down here, I have to multiply the denominator of alpha 1 by 100, okay? So I end up with alpha 1's interpretation, once we divide it by 100, as meaning the percent change in x effect on y. A more elegant way to say that is, it's the change in y in units from a 1% change in x. So in other words, to restate, alpha 1 over 100 is the change in y in units from a 1% increase in x. Okay? So let's make out what would happen if the log were on the other side of the equation. So now the interpretation of alpha 1 is d log y. We could just call that z, right? But let's leave it at log y because we're going to exploit that functional form in terms of y. Alpha 1 is d log y dx. But now we know that d log y is just the total differential of y, which is 1 over y times dy. Okay? So here we've got dy over y divided by dx. And dy over y is almost a percent change, but it's in fraction form. So we can convert this into percent terms by multiplying the numerator by 100, but if I multiply the numerator by 100 here, I have to multiply alpha 1 by 100. And I end up with what? I end up with the following. Alpha 1 times 100 is equal to the percent change in y that results from a 1 unit change in x. Okay? So if I were to get an alpha 1 equal to 0.11, what would that mean? When I multiply it by 100, I would get 11, and that would be the percentage change in y from a 1 unit change in x. Okay? Now let's look at the double log model, which is what you see in the Morgan-Kelly paper, I believe. So here we have the log of y equals alpha 0 plus alpha 1 log x, and now the interpretation of alpha 1 is d log y over d log x. But we now know that that's just the change in y over y divided by the change in x over x. And if we multiply the numerator and the denominator by 100, that's like multiplying the whole thing by 1. It doesn't change it. But we now have the interpretation of the percent change in y over the percent change in x. Or in other words, alpha 1 itself reflects the percent change in y from a 1% increase in x. And this, in fact, is an elasticity. So this is really the elasticity of y with respect to x. Percent change in y over percent change in x.